something first. Look here. You see, if I open YouTube, okay, like this, YouTube is open now. Then in this search bar, I type Sohaib Ahmed biology, okay, and then I press on this search button. This is the first you see channel. Just open this one, then press on videos over here. Now come over here, down. You guys see, look here, 1, 2, 3, 4, 5. These first 5 videos, they explain complete blood and circulation chapter. All right, boys?
Okay, sir.
Right, 1, 2, 3, 4, 5, complete blood and circulation chapter. So you can do the revision of it. Then come up over here, look here, 1, 2, 3, and 4. These 4 videos, they explain complete breathing and respiration chapter. All right, boys? Now, let me tell you your syllabus for the this final term examination. Did I tell you guys syllabus of final term examination before?
No, sir.
Yes.
Okay, let me tell you, chapter 9, 10, and 11 will come. And that is blood and circulation, pathogens and immunity, and breathing and respiration. All right. So 2 chapters, their complete video lectures are over here. You can, you see, just revise from here. Got it, boys?
Yes, sir.
Yes, sir. Yes, sir.
Okay. Now, today I am going to show you guys 2 videos which will help you guys for the revision of this uh, pathogens and immunity. Okay. Especially about immunity. All right.
Okay,
All
sir.
right, boys. Can you hear me?
Yes, sir.
Okay.
But your body is engaged in a never. You may not know it, but your body is engaged in a never-ending battle. You are literally covered in staph and strep and E. coli and all sorts of dubious characters that are intent on using you and your body's many resources to feed themselves, find shelter, and reproduce as much as they want. And hey, we all gotta make a living, but it is not your job to give these guys a free lunch. So your body has developed a 3-part policy toward these shady customers, and its enforcement is handled by your immune system. The immune system is different from all the other systems we've talked about this year in that it's not a specific tissue, organ, system kind of system. Instead, it involves a whole bunch of different tissue groups, organ systems, and specialized but widely distributed defense cells. Together, this league of extraordinary substances joins forces to perform all of the defense functions your body depends on to keep you alive in an incredibly germy world. And the first line of defense in this never-ending battle, that's your innate or non-specific defense system. Like your average frontline soldier, it's prepared to immediately engage with anyone suspicious, and it mostly includes stuff we were born with, like the external barricades of your skin and mucous membranes, and internal defenses like phagocytes, antimicrobial proteins, and other attack cells. But some enemies must be fought with special forces, and here your body can deploy your adaptive or specific defense system, which is more like your SEAL Team 6. It takes more time to call in, but it's specially designed to go after specific targets, and it keeps files on those bad guys so it knows how to handle them next time around. But today we're going to focus on your innate system and look at how it uses an arsenal of physical and chemical barriers, killer cells, and even fever to keep you healthy, proving that sometimes the symptoms we associate with illness are actually the signs that we're healing. Just because because something is simple doesn't mean that it can't be elegant. I mean, your body is capable of some incredibly sophisticated things, including defending itself from infection. But occasionally, there's something to be said for brute force. And a lot of your innate immune system's functions aren't exactly subtle. For example, your body's very first line of defense is a simple physical barrier. And it works. Like a wall around a fortress, your skin does a fantastic job of keeping out all manner of malevolent microorganisms. As long as that tough, keratinized epithelial membrane doesn't get torn open or busted up too much, you could probably, like, make snowballs out of raw sewage and still be alright. Although, no. Many mucous membranes also provide a handy physical barrier. You'll remember that they line any cavity that opens up into the germy outside world, including the respiratory, digestive, urinary, and reproductive tracts. Not only do your skin and mucosa supply simple physical protection, they also pack some serious chemical weaponry. Eat some questionable leftovers for lunch? Don't worry, your stomach is literally filled with acid, so you probably are covered. Walk face first into your coworker's nasty sneeze cloud? No worries, your nasal passages can whip up a tissue box worth of sticky mucus to help trap viruses before they enter your lungs. You've also got bacteria-fighting enzymes in your saliva and lacrimal eye fluid, and peptides called defensins in your skin and membranes that help keep bacteria and fungi from setting up shop around inflamed or scraped skin. Which, no matter how careful you are, you're gonna get one way or another. Maybe you shave with a dull blade, or you just brush your teeth too hard, and don't get me started about the dangers of bagel cutting. So when you've breached that first simple line of defense, it's time to call on your second line of internal innate defenses. This is where your body starts pulling strategic maneuvers like firing up a fever, releasing chemical signals, causing inflammation, or other defensive tactics that help identify and attack infectious invaders. Some of the first defensive cells on the scene are your phagocytes. Their name literally means to eat, and like Pac-Man, they indiscriminately chase down intruders and gobble them up. And they come in a few different varieties. First, you got neutrophils, which are the most abundant type of your white blood cells. They kind of self-destruct after devouring a pathogen, and in fact, you've probably seen piles of their little dead bodies, because that's what pus is made of. But the bigger, tougher phagocytes are the macrophages. They're derived from monocyte white blood cells that have moved out of the bloodstream to occupy tissues, and some are free types that patrol tissues looking for creepers, while others are fixed, attached to fibers in specific organs, devouring anything suspicious that passes by. So when a macrophage, in say the finger I just cut slicing a bagel, sees a new bacterium coming along, it snares it using cytoplasmic extensions, reels it in, completely engulfs it, and essentially digests it and spits the rest out. And unlike neutrophils, it can do this over and over again, like a boss. But not all your defense cells are phagocytic. You've also got cells with what is by far the awesomest name of any cell in the body, the natural killer cells. You can call them NK cells if you want to, but like, why would you do that? Anyway, these tiny assassins patrol your blood and lymph looking for abnormal cells, and are unique in that they can kill your own cells if they are infected with viruses or have become cancerous. How can they tell? A normal, healthy human cell contains a special protein on its surface called MHC1, or major histocompatibility complex, but if it's infected, it stops making that protein. And if an NK cell detects a defective cell, it doesn't swallow it whole like a macrophage, it pokes it with an enzyme that triggers apoptosis, or programmed cell death, which is pretty awesome. So those are some ways your innate immune cells handle their enemies, but how do they know where to look in the first place? So let's talk strategery. So say you're in a banana factory, and you slip on a banana peel and you scrape your knees. Your outer fortress has been breached, and the pathogens are just flooding in like orcs through Helm's Deep. Banana factories are very dirty places. Now, your body wants to contain the spread of pathogens, clean up the mess, and get healing as quickly as possible, so it cues up your inflammatory response. This is basically an internal fire alarm, only it uses chemicals instead of sirens to get the message across, and instead of smoke and fire, you sense redness, swelling, heat, and pain. For example, in the event of injury, specialized mast cells in your connective tissue send out histamine molecules, and histamine is great at calling in the cavalry. For one thing, it causes vasodilation, which creates redness and heat at the site of the injury. Now, those things might freak you out a little, but they're actually signs of healing. The increased temperature, for example, ratchets up the cell's metabolic rate so they can repair themselves faster. Meanwhile, histamines and other inflammatory chemicals also increase the permeability of blood vessels, causing nearby capillaries to release protein-rich fluids. This causes swelling, which again is actually a good thing because that leaked protein helps clot blood and form scabs, while the lymphatic system sucks up and filters that extra fluid, cleaning it up before putting it back into your bloodstream. And of course, like chum to sharks, an inflamed knee is also going to attract a bunch of local phagocytes, which find it easier to escape your now leaky capillaries, and lymphocytes that are also flowing freely, helping to destroy pathogens while also cleaning up dead cell wreckage. And don't forget, during During all this, the neutrophils have been doing their best, but they were the first wave to arrive, so by this time they're starting to die in heaps. They're triggered when the injured knee skin cells release chemicals that begin leukocytosis, the release of neutrophils from the bone marrow, where they're made, into the bloodstream. To attract the neutrophils to the damaged area, inflamed endothelial cells in the capillaries send out chemicals that act like homing devices. And when the neutrophils arrive, they cling to the capillary walls near the injury, flatten themselves out, and squeeze through the vessel walls to get to work. Your big monocytes eventually roll up to the battle and transform into hungry macrophages, replacing the first line of now dead neutrophils and basically just eating up any lingering enemies and then cleaning up the carnage. Now, all this works pretty well in most circumstances, but you may have noticed with a more major injury or an especially nasty virus or infection, sometimes your local troops get overrun. When white blood cells and macrophages run into more foreign invaders than they can handle, they let loose pyrogen chemicals that tap the hypothalamus and raise your body's thermostat, calling in a systemic fever to burn everything. The resulting temperature rise increases the metabolism of your cells so they can heal faster, and it also tells the liver and spleen to hold on to all of their iron and zinc so those things can't contribute to bacterial growth. But even then, sometimes you find yourself facing a more formidable foe. That's when you call in the specialists, your adaptive immune defenses. And to learn exactly how they save the day, you have to watch next time. But for now, you learn that your immune system's responses begin with physical barriers like skin and mucous membranes, and when they're not enough, there are your phagocytes, the neutrophils and macrophages. You also learned about natural killer cells and the inflammatory response, and watched as all of these elements saved the day when you slipped on a banana peel. Thank you to our headmaster of learning, Linnea Boyev, and thank you to all of our Patreon patrons whose monthly contributions make Crash Course possible, not only for themselves, but for everybody. If you like Crash Course and you want to help us keep making videos like this, you can go to patreon.com/Crash Course. This episode was filmed in the Dr. Cheryl C. Kinney Crash Course studio. It was written by Kathleen Yale. The script was edited by Blake DiPestino, and our consultant is... What's true in World of Warcraft is also true in your immune system. To defeat your enemy, you have to know your enemy, uncover its weaknesses, learn how to see it before it sees you. We've already talked about how your innate defense system keeps out or quietly neutralizes pathogens without too much fuss. But sooner or later, a threat's gonna come along that's stronger than what the first responders can handle. That's when it's time for the adaptive or acquired immune system to step in. While your innate system takes its zero-tolerance policy very seriously and tries to toast any foreign microbe that it encounters, your adaptive system does things differently. It has to be expressly introduced to a specific pathogen and recognize it as a threat before it will attack. As its name suggests, you're not born with a working adaptive immune system. It's slow to act, in part because it takes time for it to shake hands with so many pathogens and get to know them. These introductions may be organic, like touching a dirty faucet in the bathroom or walking into a sneeze cloud, or they may be premeditated, which is why vaccination is pretty much the greatest thing to happen to medicine ever. But once it's been introduced to a potential threat, your adaptive defenses never forget it. And this ability to remember specific pathogens is one of the key differences between the adaptive and innate defenses. Another main difference is that adaptive immunity is systemic. Rather than being restricted to a particular infection in, say, a sinus or a sliced finger, your adaptive system can fight throughout your whole body at once. And it does this by deploying one or both of its separate but cooperating defenses, your humoral immunity and your cellular defenses. Your humoral immunity, which you might not have heard of before, works by dispatching important proteins that I'm sure you have heard of, antibodies. They're made by special white blood cells, and they patrol the body's humors, or fluids like blood and lymph, where they combat viruses and bacteria moving around the interstitial space between your cells. Much of what you know or have heard about or think of when your immune system comes up actually has to do with your humoral immunity. It's why if you had mumps as a kid, you probably don't have to worry about getting it again for the rest of your life. It's also why doctors and nurses and patients who have been infected with the Ebola virus, a disease once thought to be incurable, have lived to tell about it. And it's why vaccinations work. Whether you're protecting yourself from infections or playing an MMO, one of the first steps in any good defensive strategy is to be able to tell your friend from your foe. And in the case of your immune system, that means being able to identify antigens. An antigen could be an invader from the outside world, like a bacterium, virus, or fungus, or it could be a toxin or a diseased cell within your own body. But in any case, antigens are large signaling molecules not normally found in the body, and they act as flags that get the adaptive immune system riled up. So let's say flu virus gets inside of you, and it's floating around trying to find a good host cell to start multiplying inside of. Before it finds that cell, hopefully it will be paid a visit by one of the stars of your humoral response, a B lymphocyte. Like all blood cells, these guys originate in your bone marrow, but unlike other white blood cells, they also mature in the bone marrow too. And as a B cell matures, it develops the ability to determine friend from foe, developing both immunocompetence, or how to recognize and bind to a particular antigen, as well as self-tolerance, or knowing how to not attack your body's own cells. Once it's fully mature, a B lymphocyte displays at least 10,000 special protein receptors on its surface. These are its membrane-bound antibodies. All B lymphocytes have them, but the cool thing is every individual lymphocyte has its own unique antibodies, each of which is ready to identify and bind to a particular kind of antigen. That means that with all of your B lymphocytes together, it's like having 2 billion keys on your immune system's keychain, each of which can only open one door. So part of your immune system's strategy is just to win with overwhelming odds. The more unique antibodies your lymphocytes have, the more likely it is that one will eventually find, bind to, and mark a particular antigen. Once they've matured, B cells colonize or seed your secondary lymphoid organs like your lymph nodes and start roaming around in your blood and lymph. At this point, they're still naive and untested, and they won't be truly activated until they meet their perfect enemy match. Which brings us back to the flu virus. When the right B cell finally bumps into an antigen it has antibodies for, usually in a lymph node or in the spleen, and recognizes it, it binds to it. This summons the full power of the humoral immune response, and the cell basically goes into berserker mode. Once activated, the B cell starts cloning itself like crazy, quickly producing an army of similar cells, all with the instructions for the exact same antibodies that are designed to fight that one particular antigen. Most of these clones become active fighters, or effector cells, but a few become long-lived memory cells that preserve the genetic code for that specific successful antibody. This ensures that if and when the antigen returns, there will be a prepared secondary immune response that's both stronger and faster than the first. This is key to why vaccinations are so brilliant and important, which I'll come back to in a minute. But while the memory cells are just there to hang back and record things, the effector, or plasma cells, are packed with extra amounts of rough endoplasmic reticulum, which acts as an antibody factory. These cells can mass produce the same antibodies over and over for that particular invader, spitting them out into the humor at a rate of around 2,000 antibodies per second for 4 or 5 days until they die. And the antibodies they make work the same way that the membrane-bound ones do. They're just free-floating. So they ride the tides of blood and lymph, binding to all the antigens they can find and marking them for death. Now, antibodies can't really do the killing themselves, but they do have a few moves that could make it hard for intruders to take hold. One of their most effective and common strategies is neutralization, where antibodies physically block the binding sites on viruses or bacterial toxins so they can't hook up to your tissues. And because antibodies have more than one binding site, they can bind to multiple antigens at the same time in a process called agglutination. The resulting clumps can't get around easily, which makes it easier for macrophages to come and gobble them up. And not only that, but while all this is going on, antibodies are also ringing a chemical dinner bell, calling in phagocytes from the innate immune system and special lymphocytes from the adaptive system to destroy these messy little antigen-antibody clumps. So the point of all of this in the short term is to keep you healthy, but in the long term, this process also adds to your overall immunity. The humoral response allows your body to achieve immunity by encountering pathogens either randomly or on purpose. Active humoral immunity is what we were just talking about. It's when B cells bump into antigens and start cranking out antibodies. This can occur naturally, like when you catch the flu or get chicken pox or pick up some nasty bacterial infection, or it can happen artificially, particularly through vaccination. Most vaccines are made of a dead or extremely weakened pathogen, and they work on the premise that because a secondary immune response is more intense than a primary response, by introducing a pathogen into your body, you're priming it to fight hard and fast should that antigen show up again. In the case of typically non-fatal infections like the common flu, this immunity should at least spare you from some of the most severe symptoms. But in the case of more serious diseases like polio, smallpox, measles, and whooping cough, vaccinations can be truly life-saving. Now, some antigens, like those for mumps or measles, don't really change much over time, so a few immunizations will leave you set for life. But others, like influenza, are constantly evolving and changing their surface antigens, so immunity to last year's flu probably doesn't work against this year's flu. Still, acquired immunity doesn't have to be active. Babies, for example, naturally obtain passive humoral immunity while still in the womb. They receive ready-made antibodies from their mothers through the placenta and later on through breast milk. And that works pretty well for a few months, but the protection is temporary because passively obtained antibodies don't live long in their new body, and they can't produce effector cells or memory cells, so a baby's own system won't remember an antigen if it gets infected again. You can also acquire this kind of temporary passive immunity artificially by receiving exogenous antibodies from the plasma of an immune donor. This is what recently saved some doctors and nurses who had contracted the Ebola the virus from infected patients. A serum was made from the blood plasma of other medical workers who had been infected and survived. The antibodies helped defend the patients from the virus before their own active immunity could identify that particular antigen and start creating their own antibodies. It's not the same as a vaccine, which immediately engages your B cells, but it can buy a patient some crucial, life-saving time against an infection that would otherwise quickly kill. But B cells and antibodies are only part of the immunity equation. There are plenty of pathogens that quickly worm their way right inside your cells, where they're safer from the humoral response and free to multiply as much as they like. Luckily, your immune system has yet another game plan and a new set of players ready to fight that final battle with cell-to-cell combat. Make sure you catch our final episode next week and learn all about this epic battle royale. But as for today, in our second to last episode, you learned how the adaptive immune system's humoral response guards your extracellular terrain against pathogens. We looked at how B cells mature, identify antigens, and make antibodies, and how antibodies swarm pathogens and mark them for death. We also talked about active and passive humoral immunity and how vaccines work. Thank you to our headmaster of learning, Linnea Boyev, and thank you to all of our Patreon patrons. If you are one of those people I just thanked, you make Crash Course possible for the whole world and also for yourself. If you like Crash Course and you want to help us make videos like this one, you can go to patreon.com/crashcourse. This episode was
Okay, Wes, did you observe? You see, in these videos, they explained about the physical barriers, about HCl, about phagocytes, about natural active immunity, about you see artificial active immunity, about vaccines, and about the passive immunity as well, right? So all you see all about the immunity, it was explained in this in these videos. So do you guys have any question till now?
No, sir.
Oh, sir, no question.
Right? So there was, you see, animation as well. So you see, it was useful, right?
Yes, sir.
Yes, and you see about the antigens and antibodies, everything was explained over here. Okay, boys, see you guys inshallah in next class. Take care and Allah Hafiz.
Allah Hafiz, sir.
Love you, sir.
Allah Hafiz.